Routing is one of the most influential steps in any hydrological model, and RORB is no exception. The way flow routes through a catchment can completely change flood timing, peak discharge, and the overall shape of the hydrograph. But here's the catch. Routing depends heavily on the parameters you choose. A small change in such parameters can mean the difference between an accurate flood estimate and a misleading one. In this video, I will show you how routing works in RORB, what the key parameters are and what they really do, and the tips and tricks to help you avoid common mistakes and develop more reliable models. Let's get started. RORB is a widely used event-based rainfall runoff model, particularly across Australia. Its development began in the 1970s with Laurenson and Main at Monash University. RORB was designed to bridge the gap between simple empirical methods and complex hydraulic simulations. It is an aerially distributed model that represents the catchment as a network of sub-areas. Rainfall excess is computed locally within each sub-area and then routed through a system of channel reaches. Let's start with channel routing in RORB. The heart of RORB's channel routing system is the Laurenson nonlinear storage method. To explain this, we need to refer to the foundation of any hydrological routing system, the continuity equation. ds over dt, the change in storage over time, is equal to inflow I minus outflow Q. To solve this, a second relationship is required. In the Laurenson method used by RORB, this equation is conceptualized by assuming that the storage in the channel is a power function of outflow discharge. This storage function is mathematically expressed as S equal to K times Q to the power M, where S is the volume of water stored in the reach, Q is the instantaneous outflow discharge, K is a dimensional empirical coefficient that represents the storage delay time of the reach, and M is a dimensionless exponent that defines the degree of nonlinearity in the catchment's response. Now let's see how RORB solves the routing equation discretely. First, the continuity equation can be approximated in finite difference form as this. Substituting the nonlinear storage function into this equation results in an implicit nonlinear equation for the unknown outflow Qt plus 1. Rearranging to isolate the terms, we define a function f of Qt plus 1 that must equal 0. Since m is usually non-integer, there is no direct algebraic solution for Qt plus 1. RORB employs an iterative numerical procedure, specifically the Newton-Raphson method, to solve the root of this equation at every time step for every reach. Now let's explore the routing parameters in the RORB model. First, the exponent m, which is the parameter that governs the nonlinear behavior of the model. It determines how the storage delay time, or effectively the travel time through the reach, varies with flow magnitude. If m equal to 1, the equation becomes S equal to kq. This represents a linear reservoir where the storage is directly proportional to outflow. In this case, the lag time k is constant regardless of the flow magnitude. However, in natural channels, flow velocity typically increases with depth due to a reduction in relative roughness and an increase in hydraulic radius. This behavior is valid at least until overbank flow occurs. Higher velocity implies a shorter travel time. If m smaller than 1, the effective lag time decreases as q increases. This accurately mimics the physical reality that larger flows typically move faster through a channel network than smaller ones. While studies show m can range from 0.6 to 1 depending on channel geometry, extensive empirical research in Australian catchments supports using 0.8 as the standard value for ungauged catchments where calibration data is unavailable. Now let's get back to the other routing parameter, k. A critical innovation in RORB is the decomposition of this parameter. If every reach in a model required an independently calibrated k value, the model would be massively over-parameterized and practically impossible to calibrate uniquely. To solve this, RORB separates k into a global catchment parameter and a local reach parameter. Let's know more about this. This is expressed as ki equal to kc times kri, where ki is the storage parameter for the specific reach I, kc is the empirical coefficient applicable to the entire catchment and stream network. It has units of time and effectively scales the hydrograph lag for the whole basin. And KRI is the relative delay time, a dimensionless ratio applicable to the individual reach I. This formulation allows the modeler to calibrate a single parameter Kc that shifts the entire hydrograph in time, while the relative timing between different tributaries is maintained by the fixed KRI values. First, we explore the relative delay time KRI. This parameter is typically calculated based on the physical characteristics of the reach. RORB calculates KRI by KRI equal to Fi times Di divided by DAV, where Fi is a factor depending on the reach type, Di is the reach length, and DAV is the average travel distance of the catchment, which is calculated by this formula, where Ai is the area of the subcatchment I, and capital A is the total catchment area. This ensures that the storage allocated to a reach is proportional to its contribution to the total travel time of the network. Now let's discuss the catchment storage delay parameter Kc. Perhaps one of the most studied aspects of RORB is the estimation of this parameter for ungauged catchments. Since Kc represents the storage delay of the entire catchment, it correlates strongly with the catchment size and shape. So far, researchers have developed numerous regional regression-based equations to estimate this parameter. The early works on this had Kc as a function of catchment area, where C and E are empirical constants found through regression. However, more recent studies suggest Kc being proportional to the average travel distance DAV, where C is a regional constant. For example, a study by Pierce et al. In 2002 on over 200 catchments in Victoria State suggested a C value of 1.25 for this state. Another study by Yu 1989 also suggested an Australia-wide constant of 1.14. It is noted that in these equations, m is equal to 0.8. These equations allow a hydrologist to build a RORB model for an ungauged river reach. However, it is always preferable to estimate this parameter through calibration or by adopting it from a similar neighboring catchment. While the Laurenson model is ideal for open channels, it is not suitable for distinct water bodies such as dams, reservoirs, and retarding basins, where the storage-discharge relationship is governed by topography and outlet hydraulics. For reservoir routing in such elements, RORB utilizes a special storage module. The routing method here is the level pool routing, also known as modified pulse method. To model a special storage in RORB, the user must define a stage storage-discharge relationship. This is provided by elevation versus storage data, a table derived from the bathymetric survey of the basin, and elevation versus discharge data, a table derived from the hydraulic equations of the spillways, pipes, or weirs controlling the outlet. RORB's implementation of reservoir routing includes logic to handle complex time-varying or state-dependent outlet structures such as gated spillways. This allows the user to specify operating procedures for the dams or retarding basins. Ultimately, the reservoir outflow becomes the inflow to the next reach in the RORB network. This is the advantage of RORB reservoir routing over a standalone level pool routing exercise, which generally isolates the dam from the catchment. Be mindful that, like other hydrological routing approaches, RORB's routing system doesn't account for backwater effects. Capturing those requires hydraulic routing, which is handled by dedicated hydraulic models such as two-flow or HECRAS. A critical challenge in calibrating RORB is equifinality, the phenomenon where different combinations of parameters yield the same result. For example, a similar hydrograph peak can be achieved by high rainfall losses and fast routing, or by low losses and slow routing. If the modeler chooses the wrong combination, the model might fit the calibration event but fail for a design event of a different magnitude. The rigorous decomposition of Kc and the use of regional guidance help constrain the routing parameters to physically realistic ranges, preventing the user from forcing the model to fit by using absurd routing values. So that was the core of how routing operates inside RORB. The key takeaway is this: understand the methods and their key assumptions, justify the parameters, and always run a sensitivity test. In the next episode of this series, we are shifting to another major hydrological model, SWMM. We will break down how routing is implemented there and how its approach compares to what we have seen in fundamental routing methods such as Muskingum and level pool routing. Stay tuned.